Hello, Charlie B here, and welcome to part 4 of cryptocurrency from scratch. This video we're going to be starting in on blocks, and the first thing that we're going to do is create the Merkle root. So that's pretty exciting. But before we jump into that, some housekeeping. I have put all this code up on GitHub. There is a link in the comments, in the video description. Actually, 2 links, one to this specific commit that we're going to create in this video, and one to the generic page. Also, the last video ran way longer than I wanted it to, and a lot of that was me doing the housekeeping part of this. So what I've done in this video to prepare is that I've already done the housekeeping part, and I've already have a commit up on the GitHub for that part. So what I'm going to do first of all is let's just have a look at the changes that I made. Some significant, some less significant. More imports. I created this private text to private key function. There already is a private key to text function, which I didn't use before. Now I'm using it, so I need to be able to reverse it, obviously. I added this encryption function, which is, just takes a message in bytes and outputs the SHA-256 of it. No big deal. This is some more refactoring. So what I realized was that this function, you can't incrementally add transactions to it. You have to give it the whole chain, and the whole chain is either good or it's bad, which is fine for our purposes in the previous video, but is not going to be good enough moving forward. So what I've done is, what we see is, here is the sort of running state, the set of unspent transaction outputs. And there's also implicitly a dictionary of transaction IDs. And what I've done is, instead of having this verify chain, I've got a verify transaction function, which takes a state and a single transaction. And the state is, where is it? Here, it's just 2 things. Dictionary of transaction IDs, so it's going to be the transaction ID and the transaction itself in this dictionary, and the set of unspent transaction outputs, which is exactly the same as it was before. So what this guy does is it looks at the state, doesn't change the state, looks at the transaction in exactly the same way. It's exactly the same code as this, but it just gives you true or false. It doesn't change anything. Now this verify chain function takes the state, which is probably empty for our purposes at the beginning, verifies all the transactions in it. If they're all good, if any of them are bad, it will return false. If they're all good, it will update the state variables for each transaction, or rather, for each transaction, if it's good, it'll update the state variable. And that is just copy and paste of the code from the previous one and this guy, which is filling the dictionary of transaction IDs. Okay. The other thing that I added is this function, basically a test function. It generates it generates a single random transaction based on the state, a list of transactions, and a set of key address pairs. Actually, it's a dictionary of address to private key, so that it can, sort of simulate being people and create new transactions. It does have a bug, but it's a bug that I'm going to cause to happen less often, rather than actually fixing it right now, because it's test code, so I don't care about it that much. I'll probably fix it between this video and the next, but I'm going to work around it. And then the main function, I have added these calls to update state. So we create the state at the top, and it's empty. Create the very first transaction, the Coinbase transaction, so to speak. Update state to add its transaction ID and its unspent transaction outputs. Create this next transaction, sign it just like we did before, and update the state, and the last one as well. And then I've created this address keys, which is an address to the corresponding private key dictionary, and then generating a single transaction. Okay, so let me bring this back. What I also did is add this line, which will print the transaction ID and then OK as it's verifying them. Okay, so now when I run this thing, what you should see is none, OK, 4 times for each of the 4 transactions, because we haven't put any transaction IDs in there yet. Okay, very good. Oh yeah, I need to fix this too. Oops. So the way that you make that bug that I was talking about happen less is by increasing the number of tokens that we have. So this is going to become 300,000. 300,000 instead of 30. 700,000 and 1,000,000. Okay, so we're just dividing up 1,000,000 coins instead of 100, so we can slice them a lot finer, which is the essence, in essence, what the bug was. Okay, so the first thing we need to address actually is the complete lack of transaction IDs. That is not cool. So I'm going to add a transaction ID function. Now the transaction ID is the hash of the whole transaction, including the signatures. So it's actually very similar to what we're doing here, where we take all the bytes from the transaction inputs, pub key and outputs, and sign them with each of the private keys. We're not exactly going to do the same thing, but it's the same idea. So we're going to return the B64 encoded version of the SHA-256 hash of a string of bytes, which is, just in case any of them aren't bytes, which many of them aren't, so this just translates them into bytes if they're not already. Some of them are, some of them aren't. TX inputs. I'm just basically adding the entire transaction together here. TX pub keys. TX outputs, and the transactions ID, the transaction signatures. Okay, that's that. So let's add that to this code here. Yeah. So we want to do BC -1 for the one that we just added. TXID equals TXID of BC -1. And because I used relative numbering, I can just do it here. So it's important to add it after the signature, because the signature is part of what we use to generate the transaction ID. So if you haven't signed it, you generate the transaction ID and then you sign it, they're not going to match anymore. Let's see what we end up with here. There we go. Okay. So yeah, we have real honest to goodness transactions ID there, transaction IDs there. But I also need to add that to this guy. So this is the random transaction generator. So TXID equals, again, TXID of transaction. Yeah, good. So now we can get started on the, I'm going to call it boilerplate. No, let's get started on the first part of the block. So just to give us a little bit of context, I'm going to create this make block function, which, just like the transaction one, is just going to return a dictionary. There's the header, which is another dictionary, and the transactions, which is a list. And the header, oops, the header is going to consist of a number of elements. First one of which is the number, which is the block depth, if you like. In this case, actually, it's going to be, what am I thinking? So this is the blockchain, which is, in this context, a list of blocks. So the number is going to be the length of that list. So when we generate the first block, the len is going to be 0, and it's going to be the 0th block. If we generate the first one, the len is going to be 1, because it'll have that first block in it, etc., etc. Then the previous block hash, which is actually not the correct name for it. It's actually the previous block's headers hash, but that's not important right now. Which was going to be a string. The Merkle root. Which is what we're going to talk about in a second. Difficulty, which controls the number of, controls how difficult it is to solve the block. I'm going to set it to 1. Doesn't matter right now. It's probably going to be fixed for quite some time to come. And the nonce, which is going to be 0 to start with. So these two work together. So in a nutshell, the difficulty control, so the nonce is a number, and you increment that number until the hash of the block header has a certain number of zeros in the start of it. And the number of zeros that are needed for the block to be valid is controlled by the difficulty. We'll get there probably in the next video, I think. Right now, I'm going to fill in the Merkle root. If I can type Merkle root. Now, what we're going to do with the Merkle root, or what happens with the Merkle root, is it takes a list of transactions, so these transactions, the body of the block essentially, and it hashes them. It actually hashes them twice in Bitcoin, but I'm just going to hash them once here. It hashes them, and then it takes them in pairs and adds those pairs together and hashes those, and now you have a shorter list. Does it again pairwise, hashes until you get a single value at the top. So that's what I'm going to do, and I'm going to do it recursively because I like recursion, and it's less complicated in this case. than trying to do it iteratively. There is still going to be iteration in this, of course. So what do we need to do? We are going to need to get the next level of hashes, and we're going to have to take them pairwise. So I'm going to create this variable called first, and then you'll see what I'm going to use it for in a second. For h in hashes, if first is none, then first equals h. Else, we are going to do SHA-256 of first plus h. Okay, so when we first start this loop, first is going to be none. It's going to pick up the first transaction, and then first will be equal to that first, the first hash, and the first will be equal to that first hash. Then the second iteration through the loop, its first is going to be equal to the hash, the first hash. So we're going to add that together and SHA-256 it, and then we're going to append that to next hashes. Dot append. Okay, and then we have to reset first. So that way we're going to go through and just take them pairwise. So that is going to build up. First time you call it, it's going to build a root. It's going to build a list that's half the length, potentially plus 1, of the original list, combining the hashes pairwise. Okay. And now, if there's an odd number, what's going to happen is when we get out of the loop, first is going to have a value. If first is not none, then we need to add another value, because otherwise we're going to lose data. We don't want to do that. And the way that we do this is we just double it. Okay. So if we've got an even number, first will pop out here as none, and we won't do this. If we have an odd number, we've got one hash left over, essentially, and that will be in the first variable, and then we just add that thing doubled to the list. And we have to recurse to return what we're recursing, so that when we're coming back up the stack, that we actually get a value. Next hashes. Okay. Now, it's important in recursion to have a termination condition, obviously. So if hashes, I don't really like doing this, but hey, if len hashes equals 1, then we're going to return the B64 encoded version of the first hash. Okay. Now we need to kick this off, which is why I've put a function within a function, so that in the outer function I can do Merkle root of, so it's transactions. What I'm actually doing is getting the hash, which is what I just created with the transaction ID, so I'm going to sort of cheat a little bit. Yeah, that's fine. Yeah, I guess it's okay. I'm concerned because this is actually B64 encoded, and all of the internal stuff is not B64 encoded, but do I really care? Okay, I'll decode it, it's fine. B64, 64, decode. For TX and TXs. What did I do? Invalid syntax. Oh, yeah. Something has not to be none, right? Okay. Merkle root. So let's just recap. I am getting the binary or the non-B64 version of the transaction ID from each of the transactions that we pass in. I am taking them pairwise and SHA-256 hashing each pair. And if there's one left over, I SHA-256 hash it added to itself. So it sort of creates a tree that eventually comes together in a single number, or a single string of bytes that I B64 encode and return. Or actually, I do not return it. Now I return it. So let's try to take the Merkle root of our not really a blockchain. And what I'm actually going to do for the purposes of illustration, I am going to print the length of hashes here. So what you should see is all of the stuff that you saw before, the 4 transaction IDs, and then 421, and then a Merkle root, a B64 encoded Merkle root. Really? Well, okay, I failed to terminate somehow. Let's see. Interesting. So the very first time I go in there, I totally fail to... Oh. There we go. It never even gets into the recursive code. It just recurses on itself forever. Not ideal. Fine. There we go. Let's get that. Okay. Here's our 4 transactions. They're valid. Our Merkle tree is doing 4 of them, which results in 2 at the second level and 1 at the third level, and that one is this value. So that gives us a value that if you try to change any of these transactions, the transaction ID obviously will change. Yeah, you know what? That's a bit of a problem, isn't it? So this is not, we're not just going to take it as read. We are going to actually generate the transaction ID for each of the transactions. So if you change anything in the body of the transaction, you're going to change this value. And that's got to match the transaction ID. And not that we checked that anywhere. But so if you change anything in the body of the block, so anything in the list of transactions, you will get a different Merkle root, because one of these 4 transactions will change, which will change the next level, which will change the next level, which will change the root. So that's a way of verifying that the body of the block doesn't change at all. Otherwise it wouldn't match. Let me just test that since I just changed it. Yeah, okay. Now, let's get a bit more creative. I don't care, not really creative. Let's give it a bit more of a test. So now I'm generating 50 transactions, so there should be, 53 popping out. Yeah, Good. I don't know if you can see that behind my picture. Let me just less it. Yeah, you still can't see it. Alright, let me just... so, I think you can see this part. My face shouldn't cover this. 52 transactions, 27 next level, blah, 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 all the way down to 1. So we have a value here that will not change unless the body of the block changes, which is to say we're protecting the body of the block from being able to change by putting this value in its header. Now the Merkle tree that we basically threw away as we were calculating the Merkle root is also very useful for validating individual transactions within blocks, but I am not going to cover that right now. We will get back to that. What it's really useful for is allowing lightweight wallets to verify transactions without having to download the whole block and without having to really trust the node that they're communicating with. So it's very useful, but as I said, right now we're just throwing it away and we're using it primarily or solely to verify that the block body has not changed. Okay? So next time we're going to do more work on the block. And I think next time we're going to be able to solve the block, which is mining. So that's pretty interesting. So see you in an amount of time. Thanks a lot. Bye bye.